Let's continue on the topic of radical stability. So, we talked about how degree of substitution affects radical stability. Greater substitution leads to greater stability, and that was a hyperconjugation effect. Well, as always, resonance can play a big role in stability. So, if we looked at a radical like this, let's make the other end a little different. Something like this, we could draw a resonance form for this. Now, when we move electrons in radicals, we move them one at a time. So we use these what they call fishhook arrows. But we can move this radical with this next door double bond. Of course, the double bond has to be right next door. It can't be. You can't have sp3 atoms in between. And so the radical that we showed on the left will be stabilized by the presence of another resonance form. Now, you're not delocalizing charge, but you're still certainly delocalizing electron density, and you're allowing the radical nature, this unstable, non-full octet nature of the radical to be shared between two different carbon atoms within the same molecule. Furthermore, if you're going to look at these as two resonance forms, you would say this would be the major contributor, and on the left would be the minor contributor, because this is a secondary radical versus a primary radical on the left. So, we can evaluate different resonance forms as different Lewis representations and apply our rules for relative stability, the whole 9 yards. How else can we look at radical stability? Well, radicals, I said earlier, radicals are generally considered to be electron poor. And I said that because they don't have a full octet. Here's a weird thing about radicals. Radicals are stabilized by electron donating groups. Okay, that's no real stunner. If radicals are electron poor, electron donating groups ought to be stabilizing. But they're also stabilized by electron withdrawing groups. And that's kind of interesting. We're not going to expand upon this, but that's a little counterintuitive. It gets into how the orbitals mix together, but radicals are stabilized by both electron donating and electron withdrawing groups. And if you ever forget or have a hard time remembering what are your electron donating groups, if we go back, this tends to be our ortho-para directors. Those are our electron donating groups, and electron withdrawing groups are typically our meta-directors. So, things we learned that were electron donating back in our aromatic chemistry are still electron donating as we look at other branches of chemistry. So, this is you can affect the stability of a radical. It's not just degree of substitution. Ideas such as resonance are still important, and stabilization, and actually either electron donating or withdrawing groups also will stabilize a radical.